This is a CHEM Study film, a production of the Chemical Education Material Study. With these scientists, you are looking through a 4-foot wall of water into a remotely controlled laboratory called a cave. In the cave is an ion exchange column being used to separate radioactive transuranium elements. Some of the chemical properties of these elements will be demonstrated by Dr. Burris Cunningham. Methods for their separation and identification will be shown by Dr. Stanley G. Thompson, and Mr. Albert Ghiorso will tell how they are synthesized. Each of these distinguished scientists will discuss experiments he originally did in the discovery of these elements. This work on the transuranium elements was performed under the general direction of Dr. Glenn T. Seaborg.
Since 1940, scientists have been able to synthesize and identify about a dozen of these elements. While all of these elements are radioactive, they're like other elements in their chemical properties, and therefore they can be characterized by these properties. They form compounds, they ionize, they have oxidation potentials, and therefore E0 values, and so forth. Therefore, if we know their position in the periodic table, we can predict their chemical properties. This is the periodic table as it looked before 1940. The rare earth elements, or lanthanide elements, were fitted between barium and hafnium as they are today. But thorium, protactinium, and uranium were believed to be related to hafnium, tantalum, and tungsten. The transuranium elements, or elements after uranium, were expected to fill out this role and to have properties that resembled these elements. However, when Neptunium and Plutonium were discovered, their properties were found to be much more like uranium than like rhenium and osmium. The proposal was then made that transuranium elements formed a uranide or uranium-like series, and that the undiscovered elements 95 and 96 should be like uranium in their chemical properties. Our plan was to produce these elements by cyclotron bombardment. This is a scale model of a cyclotron. When these new elements were available, we could investigate their chemical properties. In order to investigate the chemical properties of these elements, we go to the laboratory of Dr. Burris Cunningham.
Dr. Cunningham performed the earliest ultramicrochemical experiments on plutonium and many other transuranium elements. He was the first man in the world to actually see plutonium.
We're ready to perform some experiments with the transuranium elements. These experiments will tell us something about the oxidation behavior of these elements. Here are ionic solutions of the nitrates of uranium, neptunium, plutonium, americium, and curium. And here is a solution of gadolinium nitrate. Gadolinium is one of the lanthanide, or rare earth elements. As you know, the transuranium elements are radioactive. The particular isotopes that we are using emit helium ions called alpha particles. However, since alpha particles can be stopped by ordinary glass, we can perform our experiment safely in a glove box. Before we proceed, however, let us take a look at the version of the periodic table which is based on the notion of a uranide series. This arrangement suggests that the transuranium elements ought to exhibit oxidation states similar to those of uranium. Let's test this idea experimentally. We'll add a strong oxidizing agent, peroxydisulfate, to each of our solutions of the transuranium elements. We'll also add the oxidizing agent to the gadolinium nitrate. Now we'll heat the solutions and allow plenty of time for the oxidizing agent to act. Our first observation is that the solutions have changed color. This is an indication of a change in oxidation state. We'll test them to see if they are all in the same oxidation state. To make the test, we add a solution containing sodium acetate and sodium nitrate. A precipitate starts forming, which must settle before it is clearly visible. This precipitate is an indication that the uranium ions are in a +6 oxidation state. Let's continue adding our acetate solution to Neptunium, Plutonium, Americium, Curium, and gadolinium. Here are the results half an hour later. Precipitates are present in uranium, Neptunium, Plutonium, and Americium, indicating the presence of +6 ions. But no precipitates appear in the Curium or gadolinium solutions. Apparently, they cannot be oxidized to the +6 state. Our tests show that uranium, Neptunium, Plutonium, and Americium all oxidize to a +6 state. But Curium and gadolinium do not form a +6 ion. Perhaps they were oxidized to a +5 or +4 state, or perhaps neither of them was oxidized beyond the +3 state in which it started. So we see that although Curium is a transuranium element, it is not a uranide or uranium-like element. Let us see now what we can find out about the oxidation states of Curium and gadolinium. We'll add hydrofluoric acid to our solutions of Curium and gadolinium. A trifluoride of Curium forms as a jelly-like precipitate. Gadolinium trifluoride forms a similar precipitate. This characteristic precipitate indicates that both elements remained in a +3 oxidation state. The oxidation behavior of Curium suggested that there might be a better way to classify the transuranium elements, perhaps as a second rare earth series. The element actinium and those beyond were placed in this position in the periodic table. Because the elements had certain properties like actinium, they were called actinide elements. Other experiments have shown that elements of the actinide series have chemical properties that are similar to their sister members, or homologs, in the lanthanide series. Later in this film, we will see how this concept of a second rare earth series, or actinide series, in which each element is a homolog of an element in the lanthanide rare earth series, was of great value in discovering elements 97 and beyond.
Actually, one of the critical steps in the discovery of any element is its chemical identification. We must prove that it has chemical properties different from all previously known elements. Elution behavior in an ion exchange column can provide such proof.
Here we see transuranium elements being separated by this method. The material is so radioactive that a 4-foot wall of water is used as shielding. The materials are fluorescent and with the lights off can be photographed by their own light. This separation actually requires 9 hours, but with time-lapse photography we observe the entire process in 15 seconds. Such key ion exchange experiments involved in the discovery of many of the transuranium elements were performed by Dr. Stanley G. Thompson.
Separation by ion exchange is an extremely powerful yet surprisingly simple technique. We use many different sizes, but in principle all columns are the same. The column consists of a glass tube packed with an organic resin. The tube is surrounded by a glass jacket containing a hot vapor to speed up the reaction. Now let's see how the ion exchange column helps us separate and identify rare earth elements. Here's a solution containing equal amounts of tripositive ions of 4 of the synthetic elements: Curium-244, Berkelium-249, Californium-252, and Einsteinium-253. We should mention that only small amounts of these elements actually exist. For instance, at the time of this filming, there is only about 1/10 microgram of Einsteinium in all the laboratories on Earth. We're working with small amounts of these elements in extremely dilute solutions of concentration about 10 to the minus 14th molar. The level of radioactivity is quite low. Therefore, it's safe to work with them in the open. A solution called an eluent is added to flush the actinide elements through the column. Applying air pressure to the column increases the rate of flow. As the drops of eluent fall from the column, they are collected on platinum discs. Each disc receives only one drop. The discs are dried under an infrared lamp, leaving minute amounts of the elements plus solid residues of the eluent. Flaming a disc in an alcohol flame burns away the eluent residue. Finally, we're about ready to test the disc for evidence of the 4 elements which we originally mixed and added to the column. This radioassay machine will detect both alpha and beta radiation. So even if only one radioactive atom on this disc decays, the energy release may be detected. We'll insert the disc that caught the first drop from the column. The elements that we're seeking have short half-lives, so 1 minute is sufficient to detect any decay activity. A full minute has passed, and we've had no indication of alpha particles. We'll test for beta decay, then continue testing each disc in the order of the drops that came off the column. This disc contains the material from the 7th drop. And we're getting an indication of some radioactive atoms. We'll record our data and then continue counting until all the discs have been analyzed. The data we've collected can now be plotted on a graph which shows the number of atoms that decayed in 1 minute in each drop of the eluent. When the points are connected, we have 4 significant peaks. The curves show us which drops contained the elements which separated in the column. From other experiments, we know that Einsteinium, the element with the highest atomic number, came out in drops 7, 8, and 9. The next element, Californium, was contained in drops 11, 12, 13, and 14. The element Berkelium was in these drops, and Curium was in these drops. Now we see that these heavy elements are indeed separated by ion exchange methods. A good question to ask would be just why the separation occurs. We'll try to find a good answer for that. Although the equilibria involved in the column and the structure of the organic resin are very complex, we'll represent them in a simplified and stylized manner. The surface of the resin contains negative groups, originally holding positive ammonium ions. When an actinide ion surrounded by a layer of polar water molecules is present, collisions occur with the resin. Most collisions result in the tripositive actinide ion replacing 3 singly positive ammonium ions and adhering to the negative sites. The eluent is a negative ion which competes with the resin for the positive actinide ion. A soluble complex can be formed which passes down and out of the column. Now suppose we consider 2 different actinide elements in the column, Curium and Einsteinium. X-ray diffraction studies have revealed that the tripositive ion of the curium isotope we're using has an ionic radius of 0.98 angstrom units, while the ionic radius of the Einsteinium ion is only about 0.93 angstrom units. In other words, the ionic radius decreases with increasing atomic number. Hence, the charge density of the ion increases with atomic number. The ion with a higher charge density will have a stronger attraction for the surrounding water molecules. This creates a hydrated ion with a larger effective radius, so we can generalize that the effective radius increases with increasing atomic number. If hydrated ions with different effective radii collide with the resin and form a bond, the positive ion with a larger effective radius will be farther from the negative charge on the resin. Therefore, this larger ion will be less tightly held on the resin. Thus, when the eluent passes through an ion exchange column, the more highly hydrated ions will be removed first, to be followed by the other ions in order of decreasing atomic number. You recall that when the four elements were first added to the column, they were mixed together. Now let us concentrate our attention on this mixture. As the elements passed down the column, they started separating. In time, the elements separated into bands. When the material came out of the column, certain drops of the solution contained a specific element, and some of the drops were eluent that did not contain any of the elements being separated. Radioassay data then allowed us to construct a graph of elution behavior. Here are experimentally observed curves for the four elements 96 through 99. Plus element 95, Americium. And here are experimentally observed elution curves for the lanthanide or rare earth elements. When we compare the two sets of curves, we see that the curves do not correspond exactly, but the relative positions of the curves do correspond. So early in the 1950s, we saw that the elution curves of the actinide series of elements were related to the curves of the lanthanide series. Therefore, we believed we could construct curves for the then undiscovered elements numbers 98 through 103 from the curves of the corresponding lanthanides. And as we continued to bombard many targets and separate the products on ion exchange columns, we had a clear idea as to which drops should contain the new elements, if we had indeed successfully created them. Subsequently, thanks to the ion exchange methods, we successfully synthesized and identified elements through number 101. And the elution behavior of the new elements corresponded to the expected curves.
We can further appreciate the precision of these ion exchange experiments if we realize that the original discovery experiments produced such minute quantities of the new elements that they were invisible. In fact, with element 101, only 5 atoms of the new element were identified in the 101 elution position. Elements with atomic numbers higher than 101 are produced in this machine, which is called HILAC, or Heavy Ion Linear Accelerator. Here is Mr. Albert Ghiorso, who performed the key detection experiments in the discovery of elements 102 and 103, which were synthesized in this instrument.
Element 102 was discovered at the HILAC in 1958. The reaction used was curium, element 96, was bombarded with carbon ions, element 6, to make a short-lived, a 3-second isotope. In 1961, we found Americium, element 103, and this time we bombarded element 98 Californium with boron 11 ions. Boron is element number 5. Now we are prepared to try and make element 104, and we hope to make it by this reaction. We will use the same element, 98 Californium, but this time we will use carbon 13 ions to try and make this reaction go. The isotope that we will try to find is short-lived, and we will try to detect it in this apparatus that we have here.
With this instrument, called a velocity selector, and its related electronic equipment, we can detect and record the decay of even a single atom of a radioactive element, whose half-life may be so short that it cannot be identified by elution behavior.
The electrical impulses from this detector are piped to the counting area, where they are amplified and analyzed in various ways. The probability of causing the nuclear reaction to make an isotope of element 104 is so small that we may have to bombard for hours before seeing even a single decay event. Since the discovery of the first transuranium element, about 80 isotopes have been discovered in the transuranium region. And now, with the discovery of Americium element 103, the actinide series is complete.
The HILAC can be applied to the discovery of still heavier transuranium elements. These are transactinide elements, or elements beyond the last actinide element, which has the atomic number 103. They fit into the periodic table as shown here. The half-lives of these heaviest elements are getting shorter and shorter, and it is getting more and more difficult to make transactinide elements. However, it is hoped that these transactinide elements will have isotopes with sufficiently long half-lives to make it possible to study their chemical properties and their periodic relationships.